Hello everyone, uh, welcome to another video where we'll be discussing about statistical mechanics. Okay, we'll be discussing more questions from statistical mechanics. Okay, so we solved some questions in the previous class, and mostly were just questions that came in just and gate. Okay, so we'll be solving more questions here. Right now, so this question is related to phase space. Okay, so right now the question: calculate the number of microstates for a particle in three dimension three dimension that have momentum that has momentum p. Okay, calculate the number of microstates for a particle in 3D that have momentum p. All right, so what is phase space? First of all, this question is related to phase space. So we know phase space is equal to d tau is equal to dx dy dz dpx, dpy, dpz. This is a space in position and momentum. Okay, so position we got three coordinates x, y, z. Momentum three coordinates px, py, pz. So dx, dy, dz and dpx, dpy, dpz. Okay, all right. So we can write them together like dx into dpx, dy into dpy, dz into dpz. See, dx into dpx is equal to h. Okay, you have to remember this. Summation dr dpr is equal to h. So this is h into h into h, that is hq, right? So volume, see, this is for 3D, right? 3D hq. Okay, that means okay so volume space volume of phase space is how much? H to the power f. Okay, where f is your what? Degree, like f is your degree of freedom. All right, f is your degree of freedom. So volume is equal to h to the power f. I can write it as h to the power 3m. Okay, h to the power 3m, where n is what? Total number of particles. All right. Yeah. So number of microstates in phase space. The formula is number of microstates in phase space. Number of microspaces. Total volume of phase space allowed to the system. Total volume of phase space allowed to the system divided by volume of phase cell. Okay, volume of phase cell, which will be your HQ. Total volume of phase will allowed to the system by volume of phase cell HQ. Okay, so let's do this question. What is the question? Calculate the number of microstates for a particle in three dimension that have momentum p. So three dimension means we can write this is the like the phase space volume. So let's write phase space volume, phase space volume d tau is equal to dp dx dy dz integration and dpx dpy dpz integration. All right, is that right? Okay. So mm, from here, what can we do is this is your this integration is actually I can write as what dv dx dy dz is dv and this one dpx dpy dpz. So this one becomes v, okay, and px I can write as dpx I can write as pdp dpy as p sin theta dq and dpz as d phi. Okay. If you remember the volume element in suppose in R, what did we write? R square sine theta d theta d phi. You must be wondering how did I write this? So R square sine theta d theta, that means sorry dr is also there. So that is R dr into R sine theta d theta into d phi, isn't it? It's like this, isn't it like this? Like R can be here also. Okay, isn't it like this? So exactly the same thing here. Okay, exactly the sorry, this is theta, right? No, it's alright. This is the same thing, d theta. This is the same thing here. Alright. See r dr r sin theta d theta d phi. R dr r sin theta d theta d phi. So I can write it as see p, okay, p sin theta d theta d phi. So this is your p square dp. Hmm. Then sin theta d theta then d phi. We know what happens here. D phi integration is 0 to 2 pi. Theta limit is 0 to pi. This is your whatever 0 to r. So here also this is v 0 to p square dp 0 to pi sin theta d theta 0 to 2 pi d phi. Is that all right? Okay. So p square dp integration is pq by 3 0 to p sin theta. See this integration sin theta d theta d phi 0 to 2 pi. This is your 4 pi. How? Sin theta d theta integration is minus cos theta 0 to pi. This is your 2 pi. Okay, phi limit phi 0 to 2 pi is 2 pi. So this one is minus if you take out cos pi minus cos 0. This is 2 pi. So minus cos pi is minus 1 2 pi. Minus 1 minus minus 2 minus minus plus 2 into 2 pi, that is 4 pi. Okay, so into how much 4 pi, isn't it? So I'm getting this as v into pq by 3 into 4 pi. So I can, if I write it a bit properly, 4 by 3 pi pq v. This is your what? This is your phase space volume. Did you get it? Did you get it? How? Did you get how I did it? Okay, number of microstates. Number of microstates is what? If you remember, number of microstates is total volume of phase space divided by volume of phase cell, that is HQ. So total volume, sorry, volume of phase space, that is this one, phase space divided by what? Volume of phase cell, that is HQ. So total volume of phase space is your this one. 4 by 3 pi PQV, sorry, volume of phase cell is HQ. Alright, so if I write it a bit properly, V by HQ is into 4 by 3 pi PQ. This is the number of microstates, omega. Alright, yeah, that's it. This should be the answer. Okay. Suppose you are asked entropy. What is entropy? Entropy is S is equal to Kb Boltzmann constant ln omega. Just put it there. Kb ln B by HQ 4 by 3 pi PQ. Is that alright? Okay. Yeah. Alright. Yeah. So this is your question from phase space. Okay. Similar type of question. Calculate the number of microstates accessible to the photon, okay, having frequency between nu and nu plus d nu confined to a three-dimensional cavity. Three-dimensional cavity of volume B. Alright. Calculate number of microstates accessible to the photon having frequency between nu and nu plus d nu confined to a three-dimensional cavity of volume B. Try first, you first try. Number of microstates, we just calculated sorry, omega is equal to V by HQ 4 by 3 pi PQ. Okay, frequency between nu to nu plus del nu, isn't that right? Okay, so it's like nu is the frequency. So can we calculate a relation? Can we have a relation between P and nu? So P is equal to what? E by C. E is equal to PC. So P is equal to E by C. Energy is a H nu. H nu by C. So simply I can put here d by HQ into 4 by 3 H nu by C cube. See, you must be thinking it's such an easy question. No. See, this one you should know, this expression. And this expression you will only know if you have understood this one, this thing. Alright? Yeah? So yeah, this is this one. If I expand it a bit more, 4 by 3 pi HQ nu q by CQ. 4 by 3 pi V nu q by. Alright, is that okay? Okay, this is the answer for this one. Number of microstates. Okay. Okay. So, according to Let's write down number 3. There is a consider a system. Consider a system of two particles A and B. Each particle each particle can occupy each particle can occupy one of three possible quantum states. One of three possible quantum states. One, two, three. The ratio of the probability that the two particles are in the same state to that of the probability that the two particles are in different state. These questions are from ensemble, okay, which comes next after phase space. We did two questions on phase space. After that comes ensemble. Different state is occupied. Sorry, that two particles are in different states is calculated for bosons and classical particles. Okay, they are respectively the ratios are respectively respectively a 1 0 1 by 2 1 1 1 by 2 0 1 by 2. Okay, this question came in TIFR 2000, sorry, JS 2013. Okay, let's read the question two, three times. After that only we will try to solve it. Consider a system of two particles A and B. Okay? Two particles A and B. Each particle can occupy one of three possible states. One, two, three. Only one of three possible states. One, two, three. Okay. So the ratio of the probability that two particles are in the same state. For example, this is one, two, three. The ratio of the probability that two particles are in the same state to that of the probability that two particles are in different state. Okay, state calculated for bosons. First one is for bosons. Second one is for classical particles. Okay, read the question again. You try to pause the video and read the question again. Consider a system of two particles A and B. Each particle can occupy one of three possible quantum states. One, two, three. The ratio of probability that two particles are in same state to that of the probability two particles are in different state. Okay, that's the question. Okay, so how to approach this question? First of all, we need to understand what is boson, what is classical particle. Bosons are what? Bosons are indistinguishable, right? Bosons are indistinguishable. All quantum particles are indistinguishable. Bosons are indistinguishable particles. Spin, integral spin. Bosons have integral spin. Bosons and fermions. Fermions have half integral spin. Bosons have integral spin. Spin means 0, 1, 2, 3, etc. So bosons have integral spin. They are indistinguishable. Means, for example, you are taking boson, you cannot take A, B, C, D because these are indistinguishable. You can distinguish A, B. For example, red color, red ball, blue color ball, and white. So these are distinguishable. You can distinguish white from blue, blue from red. But if all are white. So this is a what indistinguishable. If we exchange the position of two balls, we won't be able to distinguish which ball is which. Okay. So these are your bosons, and these are what? These are your classical particles. Classical particles are distinguishable, and they obey which statistics? They obey Maxwell-Boltzmann statistics. Okay, Maxwell-Boltzmann statistics. Bosons obey. Bosons are indistinguishable. They obey Bose-Einstein statistics. Okay. So how would we arrange these particles? Three states in the question. Please write the question and see the question and how I am solving it. Please. Okay, so this is I am drawing for bosons. This one is for classical. We are asked the ratio of particles in same state divided by ratio of particles in different state. Sorry. Different state. Okay. Probability. Let's see. Okay. Here bosons. How many particles? Two particles are there. So two particles. How can we arrange two particles in three states for a boson? See, boson means we will symbolize them by like this. These are indistinguishable. So two particles here, two particles here, two particles here. Two particle system is over now. Now, one here, right? One here, sorry, one here. This is gone. One here. Okay, I think that will be it. Okay, so particles in same state. How many states are there? Sorry, not state. How many states are there? Three. Particle in different state. How many states are there? So different states. Three. What is the probability of particle in same state? 3 divided by how many number of total states? 6. So 3 by 6. Okay. So probability of same state is what? 3 by 6. Got it? Now, different states. This is different. This is same state. How many states are there in which particles are in different states? 3. How many total states? 6. So 3 by 6 probability. Got it? So easy. 3 by 6. This is 1 by 2. This is 1 by 2. This is cancelled out. 1. So the ratio of this one is 1. So the first answer is 1. The options like this, these ones, our first answer is 1. So option either C or A, these are emitted now, omitted, sorry. So now what? For classical particles again, 1, 2, did you get this one? Okay, 3. So classical particle, 2 particles. So classical means we will write them as A and B because classical particles are distinguishable particles. So AB here, okay, AB here, AB here. Now then, A, B here. Hmm. If AB here, BA can also be there. This is two states. AB here, so BA can also be like this. Now AB here, BA can also be like this. Okay, so how many states in the different one, 2, 3, 4, 5, 6, 6 states different. How many states same? 3. Like particles, same particles are in like particles are in the same state 3. Total 3. Particles are in different 6. Total number of states is 9. So probability of this one is 3 by 9. Probability of a different one is 6 by 9. So what is the ratio? P same by P different. Got it? So that is 3 by 9 by 6 by 9. That is 1 by 2. So the answer, another answer is 1 by 2. So the total answer is what? The final answer is 1 by 2. Did you get it? See, we have to decode the language of the question. Okay, we have to see one by one what is. So see, through one question, we discussed Bose-Einstein. like how bosons are arranged, how classical particles are arranged. Okay, we also calculate probability. Hmm. So many things are there in one question, right? So this is one question. Very good question. It came in just 2030. Okay, next question. Next, write down question number. It will be question number four. Question number question number four. Question number four is when a collection of when a collection of two level systems when a collection of two level systems is in equilibrium at temperature T T naught. The ratio of population in the lower and upper levels is 2 is to 1 when the temperature is changed when the temperature is changed to capital T. The ratio is 8 is to 1. Then what are the options? T is equal to 2 T naught. T naught is equal to 2 T. T naught is equal to 3 T. T naught is equal to 4T. So this came in just 2018. When a collection of two level systems is in equilibrium at temperature T naught, the ratio of population in the lower and upper levels is in the lower by upper 2 is to 1. When the temperature is changed to T, first it was at T naught. When the temperature is changed to T, ratio is now lower by upper. I will write it as dash is equal to 8 is to 1. So then what is the this one? Okay. So the energy levels I can lower if I can write as E1, upper I can write as E2. Okay. So the ratio of population. So for population formula is what? Population formula is N1 is equal to E minus E1 by KB T naught. Okay. This was when the temperature was T naught. When temperature was T naught. Now N2 is equal to e to the power minus E2 by KB T naught. So the ratio was what? N1 by N2 is equal to how much in the beginning? 2 by 1. So 2 by 1 is equal to e to the power minus E1 by KB T naught. Is that alright? Yeah. So if you see e to the power minus E1 minus E2 by kpt naught is equal to 2. Okay. Now again n1 dash by n2 dash is equal to how much? 8 by 1 in the second case when temperature is T. So e to the power minus E1 by kbt by e to the power minus E2 by kbt is equal to 8. Okay. So e to the power minus E1 minus E2 by kbt is equal to E1 minus E2 by kbt is equal to 8. Okay. Uh, yeah. So 8 is actually what? 2 cube. If I write in the next slide, 2 cube. 2 is how much? We do a minus cube. Yeah, that is e to the power minus 3 e2 minus e2 by dt naught is equal to e to the minus. Okay, yeah, yeah. So if I like, I can write this like this. Take the, I can equate the upper parts. Yeah, kb cancel, d1 minus d2 a1 minus minus cancel. So t naught by t is equal to 3. So t is equal to what? T naught by 3. Okay, let's see. Wait, what? T is equal to, okay, t naught is equal to 3t. Yeah, that's correct. T naught is equal to 3t. Yeah, T naught is equal to, yeah. Okay, so this is how you solve this question. Again, it was a kind of a mixture of statistical mechanics and thermodynamics. So yeah, good question. Okay, then the next question, question number 5. For a system in for a system in thermal equilibrium, the system in thermal equilibrium with a heat bath with a heat bath at a temperature T, which one of the following which one of the following equalities is correct? Okay, del by del beta of E is equal to E square minus E square del by del beta of E square minus E square. And this question came in JS 2015. For a system in thermal equilibrium with a heat bath at temperature T, which one of the following equalities is correct? Okay, so let's so from the like, we won't see the like, from the options we can see we have to calculate this and this, isn't it? Let's see. So answer, we know average energy is how much? Average energy formula is summation Gi Ei e to the power minus beta I divided by summation partition function, that is summation Gi e to the power minus beta I. Here let's take Gi is equal to 1. Okay, so summation Ei e to the power minus beta Ei divided by summation I e to the power minus beta Ei. Okay, so if you see in the left side, del by del beta of E. So let's calculate del by del beta of average energy of E. That means del by del beta of summation I Ei e to the power minus beta Ei, summation I e to the power minus beta Ei. Now then, beta is here. Beta is how much? 1 by kBt. So let's put it. Oh no no no, we don't need to put because beta is already there. So summation I into minus beta ei into derivative of this one minus ei square into minus beta ei. Derivative you try to do yourself, don't copy from your minus minus summation minus summation I ei into minus beta ei into derivative of this one, that is minus ei. Is that all right? Summation. Okay. So if you can see, this one is actually what? If I make it plus, okay, summation I. If I again minus minus, I can make it plus, and see this is repeated again, so I can take the square of this. So I can write as summation I e to the power minus beta ei minus summation ei square, because ei square is here in the upper this one, ei square e to the power minus beta ei, and what can I do? Plus this one I can take square. Okay, isn't it? It's multiplied twice, so square. So summation ei e to the power minus beta ei whole square divided by summation e to the beta ei square. Okay. So if you see carefully, this is what this is. Okay, I will write them separately. Okay. See very carefully. It's very easy. See, I can cancel this one. Okay. So now see, this one is what ei square is inside. So when summation I ei e to the minus beta ei by e to the minus beta is how much? This one. So if square is here, so what will be this one? Minus square, isn't it? E square will be inside because there is minus here. Okay. So I can write it as what? Minus e square average plus, see, this is the whole square of e, isn't it? Yeah. Okay. So the answer is e square minus this e square is there. So this is the average value of e square. Minus is there, so minus average value of e square. Now this is what exactly. Okay, I will sorry. Just like this. If you have written, it's like this. So I can write this. Can I write like this? Yeah. So this is what. Okay. Yeah. Okay. Good. So 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 these are some of the questions we did from statistical mechanics. Alright. So every session will be solving 5 questions. So that slowly we can solve a lot of questions. I will give you very good confidence. Okay. Thank you very much, and see you in the next session.